When the state of an ideal gas gets close to the critical point, or around the critical point, in the neighborhood of the critical point, um, that's when the behavior of the ideal gas equation of state kind of sort of starts to fall apart. We're gonna show you a method by which you can check the, let's say, validity of the ideal gas equation of state, and also how to make a numerical adjustment to that relationship to get closer to a accuracy, let's say, in relating one property to the other. So let's go ahead and get started so I can try to explain the basics behind the generalized compressibility factor Z. And so we are in chapter 3, and we've talked about ideal gases, right? Now, not all gases are ideal, are they? And especially the closer you get in the neighborhood of the critical point of each specific gas, the more dicey it can be. So let's go ahead and see how to adjust in the engineering world for this situation. Well, the idea is, so we recognize all these situations as commonly recognized as gases. And what we would pray for is that all of these situations, and the ones I'm showing here, most of them are going to be, yeah, absolutely. We're going to be able to treat all these images as ideal gases. Let's say P times little v equals RT. See how that can apply to open systems and closed systems alike. P times little v equals RT. Remember what R is? R is R bar over the molecular weight. But let's see where we are, and I will try to give you some examples of when the state of a gas is near the critical point, right? And so when are you green? Where you just flat don't have to worry about it. When are you yellow? When you might have to start worrying about it. And when are you red? Where all bets are off anyway. It's not a gas. All right. And so I've drawn sort of a generic pressure specific volume diagram. And you can see to some extent the vapor dome it's almost obliterated, isn't it? But you're familiar enough with it. But you see here, I have labeled the critical point of the PV diagram, and I've got a line going through a temperature line, an isotherm, a line of constant temperature going through that. And I've labeled it T equals T critical. So that's the critical temperature. This is the critical pressure here. And here's the critical specific volume. So that absolutely pins down the critical point. Okay, let's look at the green cloud first. So if you're a commonly recognized gas, if the temperature is much, much greater, I've shown much, much greater than the critical temperature, and your pressure is much, much less than the critical pressure, wouldn't in other words, you're above this line and you're below this pressure line. So if you're over here in this region, you don't really even need to check this out. You don't need to check out this Z, this compressibility factor. Now in the red, all right, if you're under the dome, or even if to the left of the dome, you're not even a gas in the first place, are you? This would be a saturated mixture, so you're not going to be able to use the ideal gas equation of state in this region anyway. And over here, you're a liquid. Your substance is a liquid, so absolutely no ideal gas relationship there. So the yellow, here's the yellows, the things where you got to worry a little bit about. When you're in the neighborhood of the critical point, that's where you got to start worrying a little bit. So you're going to have to check your critical point against where you're at, where your state is. And also, the closer you are to this vapor dome, the more you have to worry too, right? Because you run the risk of becoming a saturated mixture down in here. So I've shaded yellow clouds here near the vapor dome, and then also up in the region of the critical point. You say, okay, How do I learn what the critical point is for my particular situation? All right, well, we've got table A1, and that's where the critical temperature and pressure is tabulated for all of these familiar substances. And what I'd like to do is look at nitrogen, right? Because we have some familiarity with nitrogen, part of it because air is mostly nitrogen, but there's other industrial applications where um, uh, we buy nitrogen in pressure vessels. Like a nitrogen blanket over top of soft drinks, right? So that gas over top of your soft drink in the 2 liter containers, that's nitrogen. And so Coca-Cola and Pepsi Cola, they use huge amounts of nitrogen in their manufacturing process of their soft drinks. Okay, so let's look at nitrogen molecular. Look at this molecular weight 28.01. Well, 28 is just fine. Okay. Critical temperature in degrees K, 126 degrees K. That's cold, right? That's cold. So keep that in mind that the critical temperature, if we go back to so this critical temperature is a cold value. Now that's dramatically different than H2O. So you got to get your thinking straight about how H2O, a phase change substance, is dramatically different than nitrogen, typically a gas. All right, so back to nitrogen. Really, really cold critical temperature. Critical pressure, 33.9 bar. Okay, well, that's going to be 3390 kPa. I think that's going to 3390 kPa is 3 megapascals. That's a pretty high pressure. Okay, so cold and a pretty high pressure. All right, so keep that in your mind. So, for example, here's non-ideal gas example number 1. So I was able to snag this image. Look at this. So this chef, I believe, the chef is pouring out of a cask, a well-insulated cask of liquid nitrogen, and he's pouring this into a vat, and it's when it comes out and hits the atmosphere, uh, it immediately starts heating up, and so you can sort of see this gaseous nitrogen, sort of probably would be considered some vapor here because you can see it. But anyway, it's gassing off. So the liquid nitrogen is nearly very quickly turning into a gas, right? And that's what you're used to. But obviously, liquid nitrogen could not be considered an ideal gas, could it? It's liquid. Okay, here's example number 2, and this has to do with a company called Linde Air Products. They produce separated gases to sell industrially. Well, there's nitrogen, just like I talked about, selling to PepsiCo and Coca-Cola. Oxygen, well, that's going to be used for people surviving, so medical applications. Argon, used for that's an inert gas that's used in putting a gas blanket around the welding process to be sure you have a good quality weld. So Linde produces all of those gases. It strips out those gases from air. Air is their raw material. But what they do is they have to get that air really, really cold in order to condense these substances out of the air. Cryogenic, right? So when you see the word cryogenic application, that is your clue to start checking the ideal gas equation of state model. So I'm going to suggest that the cryogenic process that Linde uses could not be effectively modeled as an ideal gas substance. Okay, I hope you get the idea. So the process involves cryogenic cooling to very cold, which turns out to be close to the critical temperature, a low temperature. All right, let's look at extraordinarily high pressure air. High pressure air. So what's the critical point? What's the critical point of air? And so we're going to look up in our table up high. The critical temperature is 133 degrees K. What is this? 130 degree K doesn't mean much to me. If I subtract 273 from degrees K, I get negative 140 degrees C. Now I know that's cold, but I still don't have a great feel for it. But if I transform degrees C into degrees F, it's minus 220 degrees F. Now, I know darn well that's cold. I don't know anything on Earth that gets that cold, right? So negative 220 degrees F is the critical temperature of air. Okay. Critical pressure, 37.7 bar. That's 3770 kPa, or 547 pounds per square inch. Now, that's a pretty high pressure. I will tell you that the highest pressure air that I have ever had to deal with is 1,000 psi. So I was involved in installing a 1,000 psi air compressor in a Procter & Gamble plant that made granular washing machine detergent. And very high pressure, 1,000 psi air was needed in that manufacturing process, sort of to create the granules, to blow liquid out into a tower to create the granules. So 1,000 psi is the highest pressure I've dealt with, but that was at ambient temperature of let's see, 25 degrees C. So 25 degrees C compared to minus 40 degrees C. So I would have been at a high pressure, higher than the critical pressure, but much higher than the critical temperature. So it would have paid me to have checked, can I use the ideal gas equation of state for my 1,000 psi air compressor? Okay, so that would have been one example in my whole career that I could have checked for Z. Okay, so that's the idea. So looking at air. So do you see that for air at atmospheric pressure, 1 bar, that would put us, I'm kind of off scale here, but that would put us at a much lower pressure. So we'd be down off to the right, and we'd be way above the critical temperature. So we'd be way out here. So I'm trying to wiggle my cursor way off the end of the screen. So that's why we treat air at atmospheric temperatures and pressures as a gas, and we don't check air every time we analyze air situations, because we're sort of in that green area that I mentioned here a couple of slides ago. Does that make sense? I hope so. So this is an example of checking the critical point of air. So there you go. Now on to the generalized compressibility factor. So a lot of scientists and applied researchers have done a lot of research on a lot of gases, and they have developed what's called a generalized compressibility chart. And it turns out that it's very effective for checking these situations against the critical temperature and critical pressure. And so here's going to be the definition of Z. So Z is defined as P times little v divided by RT. Remember what R is? R is R bar over the molecular weight for each particular substance. So now what I want you to do is, so let's rearrange this expression for Z. Z is going to be a number. Z is going to be a dimensionless value that might be close to 1, or it might be less than 1. It might be a little greater than 1. Okay, but it's around 1 and it's dimensionless. Well, let's rearrange this definition to say P times little v equals ZRT. So you see how I've done that? See how I've simply multiplied both sides by RT. PV equals ZRT, where Z is just some dimensionless number. Now I've written down the ideal gas equation of state, the way we model most commonly recognized gases. P times little v is equal to RT. Now let's look. Let's see how these are similar. The left-hand side, they're identical. The left-hand sides are identical, The right-hand side, both have an RT in them, but there's this Z over here. So do you see that? Do you see how you could, whatever this Z is, and I'm going to show you how to find a value for Z. We're going to go through an example problem using these figures, generalized compressibility charts. That's coming ahead, okay? But do you see visually how Z, so some number that might be a little lower than 1, might be a little higher than 1, do you see how it is sort of an adjustment? It's a numerical adjustment to the ideal gas equation of state. Pretty convenient. Drawback is that it's a graphical method. All right, but do recognize this because you're going to have a number of homework problems on it. You may have a quiz question on this. You may have a test question on this. It all depends on the priorities of your instructor. So there's no guarantee that you will, and there's no guarantee that you will not have a question or a graded problem on compressibility factor Z. So let's get into some details. Want to chase you to your textbook, section 311.2, where this was defined. And then 311.3 gives you some guidance on using this generalized compressibility data and this Z chart. And I'm going to try to help you get through that. So remember the definition, P times little v equals ZRT. Okay, so the next thing is to understand, to get onto the chart, to find out your value of Z. The chart enables you to find Z. It's not the other way around. Z is never given, okay? You're always trying to find Z, all right? You have to understand what's called reduced properties, P sub R and T sub R. So new definition, but it's easy to remember. And this P sub R is called reduced pressure. This is called reduced temperature. It is dimensionless. Look at it. It's your pressure, P, divided by the critical pressure. So as long as you get your unit straight, PR is a dimensionless number. Critical pressure, that's a lookup from that table A1. T over T critical is TR, your temperature. T critical, lookup. So, of course, you want to keep both of your temperatures in absolute temperatures to get the correct value for TR, dimensionless. Okay, so this is an important slide. Understand PR and TR, the reduced properties. They're dimensionless. We've already compared our two gas models. And one thing I didn't bring up is, do you see how if Z equals 1.000, do you see that the left-hand side describes the ideal gas model, right? And so that's the thing to keep in mind. Z is a dimensionless value. And if you end up with a Z value of 1.000, that's your signal that you've got a green light. You've got an ideal gas, okay? And so thus, you can go through the drill of checking atmospheric air in this room, and you're going to discover that Z is 1.000. That means you got an ideal gas in the room. And we could do the same thing for that blue compressed air tank that I had a few videos ago, and it would be ambient temperature. It would be 25 degrees temperature inside that tank, and it might only be 100 psi. And gosh, I can't, off the top of my head, I can't think of what that is in kPa. But it's how many? It might be 6 atmospheres. Well, 600 kPa then, right? So that you will find that Z is 1.00 for that compressed air in the compressed air tank as well. So important slide. Observe how Z equals 1.00 corresponds to the ideal gas model, and Z is a dimensionless value. There's no units. Okay, so here's the roadmap for determining Z. First thing you do is determine R for your gas. R is R bar over the molecular weight. That's the first thing you do. The next thing you do is go to table A1 and look up the critical pressure and temperature. Write down your units, critical pressure and temperature. Write those down. Then you determine your reduced pressure and reduced temperature, PR. Use those definitions, P over P crit, T over T crit. got to be dimensionless. Then you're going to go to this graphical table and what you have to do is find the PR/TR coordinates for yourself. So there's no pressures and temperatures, and only PRs and TRs. Can be a little tough to find, but you can find them. You find the intersection point of the PR and TR axes, and then you read horizontally across to determine what Z is. It is simple as that. Okay, so once you found the intersection point, so this is kind of like Y and an X, isn't it? And so once you find a Y and an X, then you find that intersection point and read horizontally to determine Z, the compressibility value that's going to be around somewhere around 1. All right, so here's our table A1 we already looked at. Okay, so that should look familiar to you. Let's see, what is it? Table A1, right? Here is a screenshot of figure A1, the Z chart, the generalized compressibility chart. Okay, so here's the confounding part. Okay, let's look at the x-axis. It's reduced pressure P sub R. That's easy. So it's easy to find where you are on these vertical lines, grids. Okay, but let's look at your TR. So it's not like a y-axis. It is a family of curves, right? And so here's your TR. Starts at 5 and starts come to 3, 2, 1.6, 1.4, 1.3, 1.2. And so these are your TR values, your reduced temperature values. And for this graph, it ranges from 1 to 5. Okay, here's 1. Here's TR equals 1. So in other words, your temperature is right at the critical point temperature. Okay, so be aware of that. TR of 1 means you're at the critical point temperature. Okay. PR at 1, well, that means you're at the critical pressure. And these would be pressures less than the critical pressure. All right. So that's a pretty good view. And so once you find the intersection point for your point, then you're going to come off horizontally to find out your value of Z. Now let's look at figure A2. So you're not guaranteed to be on figure A1, are you? So here are your T over TR from 1 to 15. Okay, I'm trying to find them here on this. So same x-axis, reduced pressures. Look at that. These are much higher pressures than the critical pressure. This reduced pressure starts at 1. So here's where your pressure exactly equals the critical pressure. And so now we're looking at pressures for your substance above the critical pressure. Okay. And then, oh, here we go. Notice up here we've got yet a third graph here. I've got to move my picture here. Okay. These are TRs between greater than 5, 7, 10, 15. Okay. And these are, I'm still having a hard time reading this graph. This is TRs of 1.05 all the way up to 3.5. I think I don't like my text box there, but at least you get the idea. Oh, notice up here. So at very high T sub R, temperatures that are far higher than the critical temperature, say 10 times more, okay? Notice how these all head towards 1.0. So see how these lines are perilously close to 1.0 and hardly any of them are above 1.1, okay? Let's look down at this curve here. Do you see how most of these families of curves, they end up all coming over for low pressures, they're all at 1.0. That means you've got an ideal Z of 1.0. You've got an ideal gas, okay? And so what are you praying for? What you're doing is you're praying for your point to be somewhere close to a Z of 1.0 so that you can use the ideal gas equation of state. That's sort of the big picture here. Now, you start more and say, oh my God, am I going to have to do this for every homework problem that involves a gas for the rest of the semester? So do I need to check Z for gases for the rest of the semester? The answer is going to be absolutely not. So these commonly recognized gases in homework problems, you're going to sail through, and you're not, once you get through this chapter 3 and get your basic homework problems for Z done, you can forget about this. The only thing you remember is in engineering practice, if you have cryogenic situations, extremely cold gases, or extraordinarily high pressures of gases, that's when you need to check Z. So, but you are not going to be required to do this Z checking for the rest of the semester for gases that you read in your homework problems. Now let's go. One last thought I had was, remember, if you have a phase change substance, you don't even mess with this Z thing. So things like steam, propane, uh, refrigerant, this Z business doesn't even come into play because a phase change substance is not an ideal gas. Definitely. Are you interested in a worked out example problem? Well, I've got a worked out example problem video called Compressibility Factor Z, let's see, into Thermodynamics Fundamentals. And the other night I was rewatching my video, and my eyes got big and my eyes just about popped out because I saw a blunder that I made when making this video. It was a mathematical blunder that involved units. So there is a blunder in this video. It will not change the conclusion of my example problem. My example problem was that Z is so close to 1, we can consider our example situation an ideal gas. But there is still there is a units blunder in my work, and have not gone back to rechange my video because it does take some effort to do these. So do recognize that if you do choose to watch Compressibility Factor Z, there is a blunder in there. So what's our recap? You need to check and utilize Z when your gas is in the neighborhood of the critical point. That's kind of rare. Okay. Remember the definition of Z. Z is PV over RT. The way I remember it is PV equals ZRT. That's the way I remember it myself. PV equals ZRT, where V is little v. Okay. Think of Z as an adjustment to the ideal gas equation of state. I hope you saw that on the graph, on the graphical method, Z was there somewhere in the neighborhood of 1, which would signal ideal gas. It does involve the lookup of molecular weight at critical properties, and then finally, graphical evaluation of what is Z based on your PR and your TR, reduced pressure and reduced temperature. Okay, that takes care of generalized compressibility factor, and I'm going to put that to bed. What's coming up next is a property and a problem-solving tool called specific heat for gases, for ideal gases, specific heat for ideal gases. And we're going to define what specific heat is, what is its application. Turns out that you're going to be using specific heat to determine changes in internal energy and changes in enthalpy for ideal gases. That's where we're headed on specific heat. So I hope this quick look at compressibility factor Z helps. And I do want to ease your mind that you're not going to be checking this Z thing with these graphs the rest of your semester or the rest of your life. So you're going to get in and out of that topic pretty quickly once you get out of chapter 3.